Okay, this video is going to be an intro and some ideas about simple harmonic motion. So let's just talk about a couple of quick examples. One of them is a classic one where you have a mass on the end of a spring and you pull the mass over here and you let it go and it oscillates back and forth, back and forth. And what we could do is we can make a plot of its position versus time. So it's position versus time. What we would see is we would see it makes a sine curve. And I'm going to start it up here because it's going to turn out we're going to do cosine instead of sine. So we're going to go like this. And its motion over time is going to go back and forth, back and forth. When things go back and forth over time, we can talk about things like period and frequency. And we can talk about amplitude. And hopefully you remember from math class, one way that we can classify this equation over here is by doing something like x of t is going to be some amplitude, and you can use sine or cosine here, and then there's going to be something in front of the x, and I'm going to write it as 2 pi times the frequency times x, and then, times t, and then you're going to add in some sort of phase shift potentially. So there's kind of your general simple harmonic motion problem. The other thing that you often see for simple harmonic motion is a pendulum. So you have a ball at the end of a string and it's going to swing back and forth, back and forth. It's also going to exhibit some sort of simple harmonic motion. And there's some really easy equations to use for some real simple problems that'll come up on the AP test, but you got to know what they are and know what they're talking about. So let me pull up this equation sheet and then we'll talk about things a little bit more. So let's look down over here on the equation sheet, and there's a bunch of things that are mixed together here. And you just have to know what's what on the equation sheet. So let's talk about first this right here, this formula T, capital T stands for period. And of course, if you forget, it's up here somewhere as well. There's period right there. And that's going to be the time that it takes for one oscillation to happen. And its units are going to be in seconds. Cool? This F down here is a frequency. And that is in hertz, and that is how often or how many times per second your thing goes back and forth. And this omega down here is a familiar character. This is going to be called an angular frequency. And you might be like, well, that's pretty familiar because on this side of the equation sheet over here, is it over here or over there? Oh, that's also angular speed, it says. So they're related to each other because when things are going in simple harmonic motion, you can also say that they're sort of related to a circular motion. So we've got 3 equations for periods right here. This right here is Ts, and that's for a spring. And this will tell you what the period of the spring, the period of the oscillations if you have a spring system. And notice how it's 2 pi and square root of m over k. So m is the mass and k is the spring constant. So just popping back over here real quick. If I've got my situation where I've got my mass that's wiggling back and forth on a spring, if I know what my mass is right here, m, and I know what the spring constant is, k, then I can figure out what the period of the spring is, 2 pi times the square root of m over k. So that would just be something given in a problem. A spring has this much spring constant and it's attached to this much mass, 2 pi square root of m over k. Notice how it doesn't have anything to do with the amplitude. So for small oscillations, now if you really pull the spring back and you pull it back a huge amount and you break the spring, then it's not going to work. But for small oscillations, it's independent of the amplitude. So the period doesn't depend on the amplitude. Okay, so the next one down over here says Tp, and that's 2 pi square root of L over G, and then P is going to be for a pendulum. So this is going to be a pendulum. So in the pendulum situation down here, where's my pendulum? There it is. All you really need to know is this length of the pendulum right there, L. For some reason, they always do like a little lowercase scripty l for the length of the pendulum. And then, of course, you need to know g, good old g for gravity. Notice how the period of the pendulum does not depend on the mass. Good, so no matter how much mass you have hanging here, it's independent of the mass. And that's also independent of the amplitude. To a certain extent, it's independent of the amplitude. So what we say is for small oscillations, then it's independent of the amplitude. So just like the spring was independent of the amplitude. Also, what we need for the pendulum is we need the size of this mass to be much, much smaller than the size of the actual length of the string. So you have more or less like a point mass right here. And that's to say that if you have a mass that's bigger, so let's say I made a pendulum and I had a giant mass hanging off the end of it, then I actually have to use a different formula, which rarely comes up inside the AP test. And that is this down here, which says TPYS. And that stands for PHYS. And that's a physical pendulum. Notice how it has an I in there. And the I is the moment of inertia of this, where is it? This mass right here, about this pivot point right here. Here, let me just copy down the formula. So T, it's actually one that I don't even really have memorized. We have 2 pi square root of I over m, g, and d. Sorry, I just copied it down there. There we go. So the I is the moment of inertia of this mass. The m is the mass of the mass, obviously. And the d is the distance from the center of mass here to the pivot point. So that's d right there. So you go from the center mass to the pivot point. Once again, that's for an object that has like a big amount of mass. Or for example, you could really figure this out if you just had like something swinging, like a meter stick swinging about its point, just about a point right there. You could figure out the period of oscillation if you know the moment of inertia of the meter stick, the distance from the center of mass to the center of the meter stick, and the mass of it, and then obviously g. So like I said, this one doesn't come up very often. And then the last equation we have over here is what I had written down before, but in a little bit of a different formula. So this is the position of something in simple harmonic motion is an x max. So this is going to be the same thing as the amplitude. It's going to be the maximum position over here. So in the springs, it would be like, what's this x max? In a pendulum, it would be, what's the maximum displacement side to side in a pendulum? And then they have cosine, and then they just have this omega in there times t plus a phase angle right there. So what this, in my thing over here, I have 2 pi times frequency, and then they just have the frequency in there. So that's the difference between a regular frequency. Where's mine? Sorry about that. There's mine. There's my 2 pi f. So what this means is, a general thing to think about, where can I write this over here, is that 2 pi times the frequency is what's called an angular frequency. So the angular frequency is related to the regular frequency by a measure of 2 pi, and then this is actually going to be in radians per second, and then the regular frequency is just in 1/seconds, which is in hertz. So it's got the same units as a angular velocity. It's just a different way to think about frequency. It's an angular frequency. So the last thing I wanted to talk to you all about was how we get this formula here and where this comes from, and a little bit about where this omega kind of fits into the situation as well. So if we're going to have simple harmonic motion, which we sometimes abbreviate as simple harmonic motion, what we need is some kind of restoring force in our situation, and that restoring force should be perpendicular to the position, directly perpendicular to the, not perpendicular, proportional to the position. It's a lot of p's in there. So it's proportional to the position. The restoring force is proportional to the position. What that's going to look like is, for example, for our springs, we're going to have the force of the spring is minus kx. Remember, that's our spring force right there. So you have a spring attached to the wall. There's your mass right there. If you pull on the spring this way, a distance of x, then there'll be a restoring force backwards this way, and that's which way your force is going. And those are proportional to each other. So the more x you get, the more force you get. Just as a little side note, remember what came out of here, by the way, is that the spring potential energy is 1/2 kx squared, which is another formula that's on here somewhere. Here is your spring potential energy formula right there, 1/2 kx squared. That happened when we took the integral of both of these sides right here, this 1/2 kx squared. But what we're really talking about now is the simple harmonic motion. So you need a restoring force that's proportional to the distance that you're going away, and that's going to create simple harmonic motion. So there could be like a conceptual question that just asks, which of these would have simple harmonic motion? They would give you a bunch of force versus position kind of things. One step further here is that we can actually kind of make a differential equation coming out of this. And the way we do that is we remember that force is mass times acceleration. So if I combine these together, I'll get mass times acceleration is minus kx. By the way, the k is just some sort of constant. It doesn't have to be a spring. It can just be some linearly proportional constant right here. So you could just have some theoretical system that has a restoring force that's directly proportional to its position. But down here, let's isolate this and let's say that A is minus k over m times x. Remembering what's buried inside of A in terms of calculus is A is d squared x dt squared equals minus k over m times x. So if we're going to solve this, this is a differential equation. Sometimes they'll have you write a differential equation. I think I'll make a separate video about that and not solve it. But if we're thinking about solving this, we're thinking about some function here, x of t. X of t is some function. And that if we take the double derivative, oops, that's a t in there, not an x, then it's going to be proportional to the original function. Right? That's what this means. It means if you take the double derivative, the second derivative of it is proportional to that, and then here's this constant of proportionality over here. So the functions that work if you take the derivative twice are sine and cosine. So if I have cosine of t, then if that's my x of t equals, then x prime of t is minus sine of t, and then x double prime of t is minus cosine of t back again. So that exactly fits this over here. The second derivative is equal to the negative proportionality constant of the actual original function over here. So the solution to this one is x equals cosine, and we're going to stick inside of here this angular velocity, or the angular frequency, and then we're going to have it be times t, and then I'm not going to add in the phase shift. Sorry about that. I was just wondering if I was going to put in the phase shift or not, so I'm not going to put in the phase shift. So here's how this solution to this differential equation works. And this omega inside of here is kind of interesting. The omega turns out to be this. If you do the calculus out in the derivatives, it'll be the square root of k over m. That's what omega turns out to be. So if you do the second derivative of this, then this will pop out of here and it'll work out. What does this really mean in terms of this angular frequency right here? If we go back to the period for the spring, by the way, so the period for the spring is this, 2 pi square root of m over k. If I sort of fiddle these around a little bit, what I can figure out is that omega, this omega is going to be the same thing as 2 pi divided by the period right there. So if I take 1 over the period and then I multiply that by 2 pi, then I'll get the square root of k over m. These will flip over, right? If I take 1 over this, these will flip over. So this omega right here is 2 pi times 1 over the period. 1 over the period, by the way, is the same thing as the frequency, just a regular frequency in hertz. So what this means is this turns out to be 2 pi times the frequency, and that's why we call it an angular frequency inside of there. Okay, so don't have to worry about those details too much. Like this last part over here is just sort of for satisfaction. What we do need to remember is formula for the period, and by remember I mean just remember how to use. Remember that this is a solution for a second derivative problem, this differential equation right here. This differential equation came from the fact that our restoring force was directly proportional to the position. Good? And then just back over here for these formulas that we have one for a spring, one for a pendulum, and one for what they call a physical pendulum, which is going to be pretty rare that comes up. Probably these are going to be a little bit more useful. And then this formula over here just relates together our period, our angular frequency, and our regular frequency. So now it's up to you to go find some sample problems to do.